the screen, right?
Yep.
Okay, cool. Yeah. Thank you, Patrice. Thank you for the invitation. It's really my great pleasure to be here virtually and give a talk. So yeah, hopefully you'll not get the deja vu. So this is again joint work with Tianqi and Xiaoping, but this time we're gonna talk about something else. And this is a recent work. And the topic is what we call the deformation space of geodesic triangulation on surface. And we also build the connections between the space with one of the classical results in computational geometry, which is the Tutte embedding theorem. And after that, hopefully I can mention some of the applications of this result. And one of the applications is solving the graph morphing problem on the higher genus surface. But before I give a rigorous definition for this space, probably let me just say something about why it might be interesting and where it comes from. So when we try to analyzing these discrete shapes, I think one of the sort of a driving idea is really we try to discretize those concepts in differential geometry and develop a independent discrete theory. And we already see there are a lot of different approaches to different discrete curvatures, discrete metrics, and probably one of the dominant example is given by this circle packing proposed by Thursday. And when we try to do this discretization, we know there are at least two requirements for a reasonable discretization. So the first one is it should be in some sense finite, so we can really do computation with it. And the second is it should capture, it cannot be random, right? It should capture some essential property for the smooth counterpart. And here, that's exactly what the circle packing provides us. Because we know that for the conformal map, we can map the infinitesimal circles to infinitesimal circles. So intuitively, the circle packing map between circle packing should sort of be a reasonable approximation to the conformal map. And from this idea, we already see we have a rich theory like discrete Laplacian, discrete conformal structure, discrete minimum surface, something like that. Okay, and yeah, hopefully we're going to see more in this workshop. But I'm going to switch gear a little bit. I'm going to say something, I'm going to ask something else, which is there any reasonable object in another field differential topology of the surface we can try to discretize? And I guess there are a lot of candidates, but I'm going to only focus on one thing, which is the diffeomorphisms. So here I'm going to, I'm just use the square to give the example. Okay, and for diffeomorphisms, we know that will just be a bijection from the disk to itself such that both the map and the inverse will be smooth. And here we're going to assume that the diffeomorphism is going to fix the boundary pointwise. So then we just put all those diffeomorphisms together to form this large space. And turns out this is indeed a huge group, this infinite dimensional topological group. And this object, actually diffeomorphism of any manifold is going to be an interesting object to study in differential topology. But probably for us in application, this group actually show up in the background. Because for instance, when we try to develop theory and try to compare shapes, one common idea is really try to define certain energy for maps between surfaces, especially for diffeomorphisms. And this energy should contain some like properties contain some information about the property for the map. And when we try to find an optimal diffeomorphism, this optimal diffeomorphism is going to capture the difference between two different shapes. And I guess one of the dominant example again is really given by the Dirichlet energy and harmonic map. And it's definitely interesting to see whether we can discretize those Dirichlet energy and harmonic map between any arbitrary surfaces. But this is not what I'm going to talk about. I will not talk about how to discretize specific diffeomorphisms in this group, like the picture you see in here. But instead, I want to ask, is there any possible like candidates so that we can discretize the total space, the diffeomorphism group? And here, so first of all, diffeomorphism group is really a huge group. And when we try to discretize that, as mentioned before, we should expect there are two things. First, it should be finite in some sense. And the second, it should capture some of the basic property for the diffeomorphism group. And here, I guess, I hope after this talk, I can show that there is a natural candidate for this discretization of the diffeomorphism group. And indeed, it is finite dimension and at least capture one of the fundamental property for the diffeomorphism group, namely the homotopy class. Okay, so then let's just say what is the reasonable choice for the approximation. And this actually it's a very natural approximation, follow from the simplicial approximation theorem we know in differential topology, which is just saying that for any continuous map between two manifold, you can always find a good enough simplicial map as approximation. And here, because we're approximating the diffeomorphism, so probably we're going to assume that we're always going to use homeomorphism as approximation. And although here in the picture I only have like 3 vertices, but you can imagine that if we have like thousands of vertices, then we can get a reasonable approximation for any reasonable diffeomorphism. And here, each such a map is called simplex-wise linear homeomorphism. We're going to assume that we're going to have a fixed triangulation for this disk, and those simplex-wise linear homeomorphism are going to fix the boundary. And since it is a simplex-wise linear, and if we think about that, actually, the image of this simplex-wise linear homeomorphism will always be like straight line embedding of this one skeleton of this triangle. And like you can see from the configuration on the right, that we have 2 different simplex-wise linear homeomorphisms. But if we just think more, it's actually easy to see that you can just determine, once you determine the position of the interior vertices, because we know that's linear, so we can just do linear extension along the edge and then do linear extension along face. And this time, once you fix the interior vertices inside of this polygon, we can just do linear extension and determine a unique simplex-wise linear homeomorphism. So since one diffeomorphism can be approximated using one homeomorphism, so I guess it's reasonable to guess that we can just put all such a simplex-wise linear homeomorphism together, and this space may be regarded as a discretization for the diffeomorphism group. So this is the sort of a natural candidate for us to define a discretization for the diffeomorphism group. And as I mentioned, there is another way to really think about these configurations. Here, when we talk about a map, it seems like you have to get a domain and the image. But actually, since everything is really determined by the position of interior vertices, so we can just forget about the base points and just put all such configuration together to form your set. And this is precisely what we mean by the space of geodesic triangulation. And here are some pictures. So in the first row, we have 3 different geodesic triangulation. They have same combinatorics triangulation, and boundary are going to be the same, but they are different. You can see the length and angle are going to be different, essentially because the position of the interior vertices are different. And for the second row, they are not elements in my space X, because in the first figure, that's indeed a geodesic triangulation, but because the combinatorics is going to be different, so that's actually in another space of geodesic triangulation, not the same space as the previous one. And in the middle, that's not a geodesic triangulation, because for the planar case, that will just means that all the edges are embedded as straight lines. And in the third example, that is, although all the edges are embedded as straight lines, that's simply not a triangulation, because you have this overlappings and intersection of edges. And actually, this picture also tells us that this space is not that simple. So we can imagine that starting from any geodesic triangulation, we can just move those interior vertices around to generate other geodesic triangulation. That's very easy fact, but we cannot just do that randomly, because it's very likely that if you just move those interior vertices randomly, then you can get some configuration like the last configuration we have here. And another way to say this is, say, for instance, maybe we have 1,000 vertices, and you can just move those interior vertices such that, say, 10 triangulation can collapse simultaneously to one point. So this really tells us that the space, if we can define some sort of closure of the space, then the closure will be very complicated. Okay, so this is the intuition for the space. And to define this space rigorously, what we need is basically just as we see is a polygon embedded in the plane and a fixed triangulation of this polygon of this disk and a boundary correspondence between the triangulation and the boundary of the polygon. And once we fix those information, then we can just put all the geodesic triangulation together to form the space. And it has a lot of names like straight line embeddings or geometric triangulation. And here, probably we need to do some normalization, say for all the edge, the map should be parameterized by constant speed. And once we do this normalization, then this map is really determined by where you send those interior vertices. And of course here, everything, the boundary should always be the agree with the boundary condition. And as we see before, this is really, this space of geodesic triangulation is really equivalent to the space of simplex-wise linear homeomorphism, because starting from any geodesic triangulation, you can just fix a base configuration and you can construct a simplex-wise linear homeomorphism. Just for each triangle, that there is a unique linear map mapping this triangle to the triangle in the target. And vice versa, for any simplex-wise linear homeomorphism, the image will always be a geodesic triangulation, satisfy all the conditions we want here. Okay, so this is pretty much the definition for the space of geodesic triangulation. And here is a video, this is how we think about this space locally, starting from any geodesic triangulation, just do little perturbation for each of the interior vertices. And as long as the perturbation is small enough, then we're still inside of this space. There's no collapsings or intersection of edges. Okay, and actually this tells us that this space is a finite dimensional manifold, since we can just locally perturb all the points. And the dimension is really just 2 times the number of interior vertices. Okay, so this already tells us that this reasonable guess for the discretization for the diffeomorphism group is already finite, a finite dimensional manifold. And we'll try to use this finite dimensional manifold to approximate this infinite dimensional manifold. Okay, and then the central question is, does this space preserve some of the properties in the smooth setting? And for the diffeomorphism group, there are a lot of interesting structures for this group. But one of the fundamental property is, as a topological group, it has a homotopy type. So here we want to ask whether this space is homotopy equivalent to its discrete counterpart in the space of geodesic triangulation. And this question is really the driving problem for this project. We're going to ask this question for this case, and we're going to ask this question for other nice surfaces like round two-sphere, flat torus, and hyperbolic surfaces. Okay, and the goal for this this talk is really pretty much provide positive answer to this question in the following 2 cases. The first case is if the boundary is convex polygon, then actually this space of geodesic triangulation is homotopy equivalent to the diffeomorphism group of this polygon. And this is actually not a new result, it's a classical result proved in 1984. I'm going to provide a detailed description for this result in a minute. But we're going to prove a new provide a new proof of this old result. And it turns out this new proof is sort of a framework, and this framework can be generalized to give a proof to the cases where the surface is a Riemannian surface with negative curvature. And this is actually solve an open question proposed by the same group of people in 83. And hopefully after that, I can mention some applications of the same framework, and this framework can provide a solution to the graph morphing problem for a higher genus surface. Okay, and this framework is really based on 2 facts, and I guess those 2 facts are very simple and practical. The first one is Tutte embedding theorem. Again, I'm going to give a short introduction to Tutte embedding theorem. And second is the floater's mean value coordinates. So mean value coordinates is really in one way to give a parameterization for a disk. And this is very important, convenient to generate surface parameterization. And we're going to see detail for this part. Okay, so but before that, probably let me just first talk about what we know about this space of geodesic triangulation. So this really, the first rigorous investigation about the space is given by Cairns when he try to study the sort of a smoothing problem for triangulated manifold. And he proved that if the boundary is simple, the boundary will just be a geometric triangle, then this space, no matter how complicated the triangulation of this triangle is, going to be a connected space. And then we can have some improvement by Ho, Bin, Starbird. Basically, Ho's result proved simply connectedness from the improved the result, and the Bin, Starbird removed the boundary condition to like the star-like boundary condition. But they are not, so all these results didn't identify the homotopy type of this space. And eventually the result by Bloch, Connelly, and Henderson really showed this. The space of geodesic triangulation is contractible. And here contractible means that is homotopy equivalent to a point as long as the boundary is a convex polygon. So this really answered the question we're going to see in a minute. This really answered the question about homotopy type and sort of show that this space is indeed a reasonable discretization for the diffeomorphism group. Okay, and actually they show more, a little stronger results. They shows that the space is not only contractible, but homeomorphic to some Euclidean space. Again, the dimension here is really just 2 times the number of interior vertices. And yeah, this result in some sense is exactly something we should expect, because we know in a smooth setting, Smell actually proved that the diffeomorphism group is a contractible space. So their results by Bloch, Connelly, Henderson actually confirms that we do have these nice connections between the smooth diffeomorphism group and its discrete counterparts. They are homotopy equivalent. Okay, I think we have a few questions. Oh, no. Okay. And just a remark that all those results, the proofs are based on the induction, of number of vertices. But right now, I'm going to provide a new proof, which is not based on induction. We're going to use the Tutte embedding theorem. So let me just say something about the Tutte embedding theorem. And the Tutte embedding theorem is really try to answer a very simple question. It's actually the title of the paper by Tutte is how to draw a graph. So the question is, if we have a planar graph, a reasonable planar graph, and we try to embed that such that all the edges are embedded as a line segment. So is there a canonical geometric representation for this graph? And it turns out there is a very simple and practical method to solve this problem proposed by Tutte. The idea is, again, very natural. For any planar graph, let's just pick a face and claim that face as the outer face, and then just fix the boundary of that face as a convex polygon, like the picture on the left. And then we can just regard all the edges as ideal springs. So ideal springs, like if there's no force acts on the spring, then the length is going to be 0. And you can just start from some configuration like that. You can start from some configuration like that, and then you just let it go. And since we know this is really the Hooke's law for the springs, we know the energy for each spring and actual energy for the spring system is really quadratic in terms of the edge lengths. So it's easy to see that we're going to have a unique minimizer corresponds to an equilibrium state of the spring system. And Tutte embedding theorem just claimed that this minimizer, this equilibrium state, will always be an embedding of this graph. And of course, all the edges should be embedded as straight lines. And this really, Tutte embedding theorem is really useful in computational geometry. And we're going to mention in a minute that this is really sort of a discrete version of a classical result of a harmonic map starting from one disk to the target. When the target is a convex disk, then if we have the boundary is homeomorphic, then the harmonic extension will be homeomorphic. This is the result proved by Riedel, Neitzer, and Chopin. Okay, and here is the detailed step for this Tutte embedding. It's actually very straightforward. The step 1 is choose the spring. So for the spring, we can have different spring constant for each edge. And here, actually, I'm going to assume 2 positive numbers. So they are just the Hooke constant. But the 2, maybe they are the same, maybe different. positive positive Hooke constant for one spring. So this is sort of a non-symmetric version of the previous energy, but and then we can just normalize this weight around each interior vertex. And the normalization step is really not necessary, but I want to point out here is we really need this non-symmetric weight to give a new proof of this contractibility of the space of geodesic triangulation. I want to show you one example where the symmetric weights would, like the energy method will not work. Okay, so step 2 is, again, independent from step 1, which is fix the boundary vertices as a convex polygon. And step 3 is we try to find where are the interior vertices. And by solving this linear system for each interior vertex, we're going to have such a linear system. And if you look at this linear system, this is really just like, essentially it just says that the image of vertex I is always a linear combination, sort of a convex combination of the image of the vertices in its neighbor. So this property can be regarded as sort of a discrete version of harmonic mean value property for the harmonic map. And another way to think about that is the equation on the right. If we just think about all the vectors starting from one interior vertices, then those vectors are in some sense balanced because they're never contained in a half space. Okay, and such a map is also called convex combination map. And here in the first row, if we think about map, natural simplified linear map from the left to right, that will be convex combination because all the vertices, if we look at the image of all the vertices, that's indeed in the convex hall of its neighbor. And if you look at the second picture in the second row, that will not be a convex combination map because the red vertex is not in the convex hall of its neighbor. And as this picture indicates, it seems like we really don't have embedding, right? There are some overlapping of triangles and intersection of edges. And it turns out that this is exactly the case. This is exactly the statement of the Tutte embedding theorem. So basically it's just saying that if we just go over those 3 steps, and in step 2 and step 3, they combine to form the linear system. And the solution to this linear system, once we solve the interior vertices, we just connect the interior vertices with other vertices based on the triangulation using line segments. And the Tutte embedding theorem just claimed that the result will always be geodesic triangulation. So there's no intersections or triangulation just degenerate to one line. And here is a quick look about the coefficient matrix. And it turns out that this matrix is always invertible, assuming that there's some minor issue about the triangulation, but it can be really reduced. So, okay, so this is the Tutte embedding theorem. And as we mentioned, this can be regarded as a discrete version of the classical result about harmonic map from disk to convex disk. And it has a lot of applications. Actually, I think Professor Yanwen Luo and Nadal shows that after subdivisions, this Tutte embedding map, piecewise linear map, can converge to the harmonic map in the smooth setting. But yeah, so this is the introduction for Tutte embedding, but I'm going to use Tutte embedding in a different way. Instead of thinking about this as a map, we're going to use this map to show the contractibility. So when we try to show the space of geodesic triangulation contractible, then we just need the basic idea is we're going to try to construct a space, and that's the space of the admissible weights here, and try to show that the space of weights is homotopy equivalent to the space of geodesic triangulation. And here are the definition for the space of weights, but actually this is really nothing but the coefficient matrix here you can get by looking at the linear system in this Tutte embedding. So this is like all the possible spring system you can get following step 1, 2, and 3. And so you can see it's really based on the combinatorics of this triangulation and also the normalization. Okay, one simple observation is this space is a subset of the Euclidean space. And since all the requirements is like either is linear equation or linear inequality, so clearly this set is really a convex set, so it's contractible. So the goal is we try to show that this space is homotopy equivalent to the space of geodesic triangulation. We need some maps. We need the homotopy equivalent. And one map is already given by Tutte embedding theorem. So Tutte embedding theorem claims that for any such a reasonable weight, actually you don't really need to do the normalization. For any such weight, you can generate a geodesic triangulation. Once you solve the linear system, the solution will always be an embedding. And of course, this map is continuous because linear system just depends continuously on the coefficients. Okay, so the remaining goal is really we need a map going to the opposite direction from the space of geodesic triangulation to the space of weight. And this is what we call the section from X to W. And the section really means that if we start from any given geodesic triangulation and we try to compute such a weight, such that once we solve the linear system in the Tutte embedding theorem using this particular weight, we can get this geodesic triangulation back. So this is the definition for the section. And it turns out there are many different choices for the section. You can take the average, you can take some sort of the center of mass. And here is a very explicit section given by floaters called mean value coordinates. And the formula looks like this. So this basically just saying that for a given geodesic triangulation, let's just take a look at each interior vertex. All right, it's going to look like the picture here. So it's going to be a star of this vertex. And then we can just compute this Cij, this weight based on the geometry, based on the angles and lengths of this geodesic triangulation and normalize it. And this is a very straightforward computation to check that if we solve a linear system using this Wij as the coefficients, then the result will be exactly the same as what we begin with, as the picture we have here. So this really guaranteeing that we have the mean value coordinates defined here is really give us a section from the geodesic triangulation to the space of weight. Okay, so once we have this, and we already we can get a very short proof of this contractibility. So essentially just argue that those two maps going to give us the homotopy equivalence. And the first one is trivial since sigma is really a section. So we're going to get the identity once we compose this with the map psi, which is given by the Tutte embedding. And another direction is really because the space W is a convex set. So we can, for any two maps, we can just use linear interpolation, linear homotopy. And this really shows that the space of geodesic triangulation is homotopy equivalent to the space of weight. And the space of weight is convex, so it's contractible. So the space of geodesic triangulation is contractible. Okay, so this really proves that the Smell sort of a discrete version of the Smell theorem. All right, so this is the new proof. And if we summarize this, this is really just this one framework, right? We just need those three things, a convex set, the space of weight, and then two maps from the space weight to space of geodesic triangulations, one given by Tutte embedding, another one given by the mean value coordinates. Okay, and this framework turns out, I'm going to mention two things. First, is generalized to the surface of the case of surface negative curvature, and the second is it also gonna give us a algorithm to compute a morphing from one graph to another on higher genus surfaces. Okay, so to generalize this to surface of negative curvature, we need to generalize this two things, right? Tutte embedding and mean value coordinates. But actually, we don't need to do anything to the mean value coordinates, because although this time for a surface of negative curvature, we don't have those nice coordinates, all the angles, but all the angles and all the lengths are still well defined. So we can still use that formula. And in some sense, we're doing this computation in the tangent space level. So we can still use the mean value coordinates as a section from the space of geodesic triangulation to the space of weight. But then the crucial thing is, how do we generalize the Tutte embedding theorem to the surface of negative curvature? Okay, and I should point out that this question is actually asked by Tutte himself. This is sort of the last section in Tutte's paper. And look at that, he asked, how do we generalize this fact to the surface of higher genus? Okay, So before I formulate the embedding theorem, probably let me just define rigorously what's the space of geodesic triangulation for the surface with negative curvature. And because here is a topology, the topology is not trivial, so we need to be a little bit careful. But actually, the idea will be exactly the same. So we just start with a surface, a closed orientable surface with negative curvature, and fix a triangulation. So here, triangulation is not only a combinatorial triangulation, but actually fix a homotopy class of maps from this polyhedron or carrier of this triangulation to the surface. And then we can just replace all the previous result, like replace the straight line by geodesic and put all the geodesic embeddings of this one skeleton of this triangulation to the surface together to form the space of geodesic triangulation. And again, we need to emphasize this is all the maps should be in the same homotopy class. And once we normalize this map, saying that for every edge should be sort of parameterized by constant speed, and then this map going to be really uniquely determined in some sense by the position of the vertices. But actually, we cannot say that the position of the vertices will singly determine a geodesic triangulation in this scenario because the topology is more complicated. But what we can say is we can just lift everything to the universal cover. And in the universal cover, the position of the interior vertices, actually everything going to be interior vertices, it's going to determine a unique geodesic triangulation. Although sometimes it will, if we just move those points randomly, will not generate geodesic triangulation, just like the planar case. Okay, so this is the definition for the space of geodesic triangulation. And of course, the natural question is, does this really give us a reasonable discretization? So we already see that this is a finite dimensional manifold. And then the question is, does this space have the same homotopy class as the smooth counterpart? And here, the diffeomorphism group S is the diffeomorphism of the surface such that it's isotopy to identity. So again, there is a mapping class group action on this geodesic triangulation. So we want to rule that out, or only care about what happens in one homotopy class. Okay, so this is the question and sort of a generalization of the question we ask for the planar case. And in this case, for the smooth setting, we know this proved by Earl and Hughes, and the space is again contractible. So the goal is really we try to prove the space of geodesic triangulation is also contractible, and then we affirm again in this case they have the same homotopy class. Okay. So then we can formulate the Tutte embedding. As we mentioned, to prove this fact, to prove the contractibility, we don't need to do anything for the mean band coordinates. We just need to generalize Tutte embedding theorem. And here is how we're going to formulate the Tutte embedding theorem for the hyperbolic or surface with negative curvature. So here actually I have two definitions. First is a geodesic map. That's a generalization of the simplicial map. That just means that for any like edge of the triangulation, it's just embedded as a geodesic arc parameterized by arc length. And notice that this geodesic map is not always be will not always be embedding, just like the picture we see, the second picture in this page. That's the picture in the planar case, but we can still say that that's a geodesic map, right? Every edge is embedded as a straight line. But it's not embedded, again, because you can have some overlappings of triangles and edges. And we can imagine this can also happen on the surface of negative curvature or even more general surfaces. Okay, so for each geodesic map, we can ask, we can make the following definition, the W balanced. So this definition is really the generalization of the convex combination map we have for the planar case. But this time we don't have a nice coordinate system for the whole space. So what we have to do is just look at the tangent plane of each of the vertex in the triangulation. So the idea is for any triangular geodesic map, we look at each of the vertex, and for each vertex, say there are 6 edges, 6 geodesics coming out from this vertex. And then we can just use the inverse of exponential map to pull back those geodesic arcs to the tangent plane. And then there will be some vectors in the tangent plane. So then it makes sense to add them together and of course, the sum is weighted sum of the given weight W. And then we can ask whether this is equal to 0. And again, if this gives us 0 for any interior vertices, then we just have this definition. We call this geodesic map is W balanced. And again, go back to the planar case. This is really just the same thing as saying that this map is a convex combination map, and the weight is a given weight W. And if we formulate the Tutte embedding theorem, say using the, using the language we have here, it's basically just saying that for any weight, reasonable weight, positive weight defined on the direct edge, there is a unique geodesic triangulation of a given convex polygon by solving that linear system, right? So given arbitrary weight, there is existence, uniqueness, and the embedding part. So that's precisely how we're going to generalize this embedding theorem in this case. Okay, so here is the formulation. We have, so here the surface, we're going to assume that it's going to have a negative curvature. And that's basically because for any geodesic or for any edge, we want to make sure that once we fix the 2 vertices in the universal cover, there is a unique geodesic connecting these 2 vertices. So this is really a finite dimensional manifold. And then we're going to assume that the triangulation here, specifically, we're going to assume the triangulation is a simplicial complex. And then we can define the corresponding space of our geodesic triangulation X. Okay, and then the formulation for the Tutte embedding theorem is there exists a unique W-balanced geodesic triangulation in space. This is precisely the statement we have in the classical Tutte embedding theorem. And this result is actually not the first result to generalize Tutte embedding theorem in this setting in the surface of negative curvature. Actually, the early result by Colin Dividier and Joe and Peter Scott already considered this problem, but their approach is sort of a variation approach. And the matter is we define some sort of a discrete version of the Ricci energy is weighted sum. Again, all the weights here are going to be positive. So that's a weighted sum of the length square of the embedding of any embedding of the one skeleton of this triangulation. And then as long as the surface has a negative curvature, then this energy in some sense will always be convex. So we're going to have a unique minimizer. And it just shows that this minimizer will again produce a geodesic triangulation. So no intersection of edges and the collapsing of triangles. And in terms of our language here, if we think about this energy method, this energy really means that for every edge, you only define one weight, right? This is really like exactly the same scenario as the planar case. You think about all the edges as ideal springs, but this time you just have those edges embedded in a surface of negative curvature. And you can start with arbitrary configuration, just let it go. And as long as this energy is convex, so eventually we're going to hit a equilibrium state. And this result just claim that on this surface of negative curvature, no matter how complicated the topology is, the minimizer will always be a geodesic triangulation. So here, the weight has to be symmetric. And our result here basically just generalize this case from the symmetric weights to non-symmetric weights. And it turns out that this is crucial for us to prove the contractibility. All right. Okay, so yeah, unfortunately, I guess I cannot talk about how to prove this theorem. I guess that will take another 2 talks. So let me just briefly mention there are 3 parts: distance, uniqueness, and embedding part, the triangulation part. And the triangulation part, to prove this is, again, embedding, actually we used a similar result as the argument given in the paper by Connelly. Essentially, we analyze how the triangle can be degenerate and use Gauss-Bonnet theorem to get a contradiction. And for the uniqueness part, that's given by some sort of a discrete maximum principle on the one skeleton of this triangulation. And the existence part is probably the most technical part. We need some topological argument to show this, and basically just a degree argument. Okay, So I'm going to pretend that you are convinced, and then we can show this contractibility, basically just word by word repetition of the planar case. So once we have this Tutte embedding, and there is a section defined by using the mean value coordinates, and once we have this well defined, we're going to have the one direction is okay. Another direction again is given by linear homotopy, because the space of weight. This time I didn't do the normalization, but actually you can do that. In either cases, the space weight going to be a convex set, so we can always use this linear in the idea of linear interpolation to construct this homotopy equivalence. So once we show that indeed the space of weight is going to be homotopy equivalent to the x, so that will be contractible. And this again affirms in the smooth setting we know by Earl and Use the space of diffeomorphism group of this homogeneous surface is going to be contractible. And here the discretization of the space of geodesic triangulation is also contractible. So this again shows us that the space of geodesic triangulation is a reasonable discretization for the diffeomorphism group. Okay, so, and this is actually not the first result. In the same paper by Joe and Peter, they show that the space of geodesic triangulation is contractible if the triangulation is a one vertex triangulation. So here the concept of triangulation is a little bit more general than simplicial complex, because we can glue one triangle with one edge of a triangle with another edge of itself. But here assumption is as long as the lift of this triangulation to the universal cover is simplicial complex, it should be correct. And that's although in our proof we make the assumption that the triangulation should be simplicial complex, but we believe that even in the more generalized geodesic triangulation case, that this space is still contractible. Okay, so this is the second part. We again provide the positive answer to the question. Now the space of geodesic triangulation is homotopy equivalent to the space of surface diffeomorphism. And as I mentioned here, I want to provide one example. This example is really show us that the non-symmetric sort of a symmetric weights is really not enough to prove the contractibility. So this is a very simple example. And why is that? So one idea is let's just use all the space of symmetric weights and only consider the sort of a minimizer of all the energies. But this configuration shows us that actually you cannot realize all the geodesic triangulation using minimizer of energies. In this picture, you can imagine that you can just rotate the triangle in the middle, right? And then all the edges for the inner triangle will not change because we're going to rotate that. That will be isometry, and all the other edges is actually going to be shorter than as long as the rotation is counterclockwise, right? We can rotate back. So this really gives us a sort of a vector field construction such that no matter what kind of energy you defined for this figure, you can always sort of decrease the energy by rotating counterclockwise, no matter what kind of weights you put for each of the interior edges. So it's just saying that this configuration is never a minimizer of energy, discrete derivative energy. So this shows that symmetric weights is not enough. We have to use non-symmetric weights. Okay, so this is sort of the end for the second part. And then let me just mention one application of this result. So again, the same framework gonna solve this problem. This is the graph morphing problem. And this problem is very easy to state, given that, let me just use the planar graph as example. So given any planar graph, we can have different geometric representation in the plane, right? We have one representation on the left and another representation on the right. And the question is, can we just construct a morphing or continuous deformation from the figure on the left and figure on the right? And if there is no restriction, then I guess there are even many different solutions. But the requirement here is during this morphing, we want to make sure that all the embeddings will still be straight line embeddings. So here, all the edges during this morphing should be still as embedded as line segment. And here is a very naive try to solve this problem. Let's just do linear interpolation of the corresponding vertices directly. And it turns out sometimes it's going to work. Actually, this video, I generated this video by doing linear interpolation of the vertices directly inside of this geodesic triangulation. But actually, for more complicated cases, you can imagine that if you do sort of linear interpretation directly using those vertices, you can create intersection of edges or collapsing of triangles. Especially, you can start with some symmetric figuration like squares. So it turns out that we cannot do linear interpolation of the vertices directly. You're going to generate some degenerate cases. So then the question is, what can we do here? How can we construct this morphing from any given graph to another one? And here all the examples, I will always use triangulation because for any graph, it's not a triangulation, you can add more edges to make that a triangulation. Okay, so, but first of all, we can just try to translate this question using our language. This morphing, this deformation actually just corresponds to a path connecting those two elements in our space X, because those two elements are two different geodesic triangulation with the same common products, right? So there are two different elements in the space X. And because we require that in the morphing, everything should stay as a geodesic triangulation. So this morphing really corresponds to a path connecting those two configuration. So this is just saying that to solve the graph morphing problem, pretty much this is equivalent to show that the space of geodesic triangulation has to be connected. Otherwise, you cannot solve this problem. Okay, and it turns out the framework we mentioned before provide a very convenient solution to this problem. And the idea is, since we cannot do linear interpolation directly in the space of geodesic triangulation, like directly linear interpolate the corresponding vertices, let's just first lift everything to the space of weights. Essentially, if you cannot do linear interpolation for the geodesic triangulation, this basically just tells us that the space of geodesic triangulation is not convex, right? Linear interpolation can generate degeneracies. But here, once we lift this to the space of weights, we know that space of weights is convex. So we can just do linear interpolation for the weights first, and then apply the Tutte embedding theorem. For any given such a weight, the Tutte embedding theorem is going to guarantee that once we solve the corresponding linear system, this is going to give us a reasonable embedding of this reasonable embedding, right? There's no degenerate. So this really gives us a path in the space of geodesic triangulation, starting and ending at the corresponding given geodesic triangulations, tau1 and tau2. So this is really a very quick way to solve this graph morphing problem using the Tutte embedding theorem and floaters in value coordinates. And this framework is actually proposed by Floater and Gottesman, but I'm pretty sure I'm missing a lot of literatures here. The thing I want to point out is this matter, based on our results, we already generalized the Tutte embedding theorem to the cases of surface of negative curvature. Then we claim that this, we believe that this framework can work to solve the graph morphing problem on heterogeneous surfaces. Basically, just pick a, say, hyperbolic metric. Probably that's the best metric you can imagine on a hyperbolic surface, on the surface. And given any two geodesic embedding of the graph, we can just first lift everything to the space of weights and do the linear interpretation, and then apply the Tutte embedding theorem. So, but here, of course, the Tutte embedding theorem is much harder because we don't have a linear system to solve. So this is really something we need to think about how to do this minimizing procedure, how to really compute this Tutte embedding. But once we can compute that, then we can really get a path in the space of geodesic triangulation. And this gives us a morphing from first geodesic triangulation to another. So exactly the same framework going to work. Okay, so, but I guess I should mention that computing the Tutte embedding theorem is already very meaningful in some, because in some sense, the Tutte embedding theorem is really just sort of a discrete version of harmonic map. So we are really computing the harmonic map in the discrete setting. Okay, so this framework works for hyperbolic surface and provide the solution to graph morphing problem. So it's very natural to ask, does this work for other surfaces? And probably it's too good to be true for the spherical case because this positive curved and we don't even have a unique geodesic connecting two vertices. But how about the flat torus case? Does this framework work for flat torus? And it turns out that this does not work for flat torus. And this is pointed out by in a paper by Chambers, Erickson, and parts that they point out that the existence part of the Tutte embedding theorem is not true for the flat torus case. That's basically saying that you can just choose some special weight, non-symmetric weight part in particular, such that you can never find a geodesic triangulation realizing that weight in the tangent space. And here, let me just give a simple example. This is a one-dimensional lower, right? A one-dimensional torus is just a circle. So here, I have a triangulation of a circle, just three vertices, A, B, and C, and I lift everything to the universal cover. And then I'm going to construct a weight, and the weight is very easy. For all the direct edge going from the left to right, the weight is going to be 3/4. And all the edge going right from the left, that will be 1/4. And then let's assume that in the starting point, in the starting configuration, all the points are evenly spaced. And then we just let it go, right? That's just exactly sort of a spring system, but this time the spring is special. The spring constants are different in different directions. And then we can even imagine what's going to happen, right? Because the force on the right side, say, let's look at vertex A, the force dragging A to the right is always larger than the force dragging A to the left. And similarly for the point B and point C. So this really gives us the following intuition. All the points A, B, C, and all the other lifts going to move to the right, all the way to the positive infinity, and never stable, never get a equilibrium state. So this really tells us that there's actually no solution to this. If we try to solve this linear system using this particular weight, there will be no solution. It's very easy to check this fact. I mean, this is really just a 3x3 linear system. So you can easily see that there's no solution once you write down those balanced conditions. Okay, and of course, this is one-dimensional case, but you can easily just make a product, say in Y direction, you do exactly the same thing. So then those weights will not be realizable. So that this weight is, there's no existence part for this particular weight. So this tells us that the existence part of the Tutte embedding theorem is not true. But luckily, they can, in this paper, they can get around this problem and still provide our algorithm to solve the morphing problem on the flat torus. But the idea is, although for non-symmetric weight, like the example I mentioned here, is not is somehow not realizable, but for the symmetric weight, is actually given by the Colin de Villier's paper. It's always, the minimizer always exists, and it's always going to give us a geodesic triangulation. So using this fact and combined with some technical discussion, they can provide a solution to the graph morphing problem on any flat torus. Okay, but unfortunately, in this case, we can, the same framework we mentioned here does not work for the torus. And that means we cannot use that directly to identify the homotopy type of the space of geodesic triangulation on the flat torus. So here is a very short summary about the result we have here. So this is really a conjecture by Connelly, Henderson, Ho, and Starbird, the same group of people as we mentioned in '83, when they finished the proof of the contractibility of the space of simplified linear homeomorphism for the convex polygon. And their conjecture is these connections, this relationship holds for other nice surfaces like the round two-sphere or flat torus or hyperbolic surfaces. And right now we know that for hyperbolic surface, that special case of surface and negative curvature, the space of geodesic triangulation really is homotopy equivalent to the smooth counterparts. So it's a good approximation, discretization for this diffeomorphism group. Okay, and we already see why this framework doesn't work for the torus, but one idea is probably we can try to characterize what happens, like what is the space of realizable weight, and then try to identify the homotopy type of that space. But for the spherical case, it's completely open. So in the smooth setting, the diffeomorphism group deformation retracts to the SO3, the orientation preserving isometries of the sphere. And there are some choice, but really this is completely open at this moment. And the Tutte embedding theorem is definitely not enough to provide a solution like this. So I really appreciate, I mean, I guess this workshop is really the best place for me to learn something, to get some new idea and try to think about this problem from a different viewpoint, and especially during this pandemic. So hopefully after this pandemic, we can really meet face-to-face, exchange ideas, and try to solve this problem together. And I guess most importantly, get some free food. Okay, so I'm gonna stop here.
Thank you, Yanwen, for this very comprehensive and very interesting analysis of this space of
yes.
and the relationship with the Tutte embedding.
Thank you.
Questions? I saw quite a few questions from.
Yeah, so I'm not sure whether that there are questions or some announcements, so I didn't stop.
No, that's perfectly fine, and I think
okay.
It's it might be good if Stefan were to ask those questions now.
Yeah, that's actually a very nice question about this geometric structure on the space of geodesic triangulation. Actually, we don't know that. We don't know any geometric structure on the space, and that would be very interesting to see whether we can induce some geometric structure on the space.
The motivation was the morphing, whether one could interpret that as essentially a geodesic of some sort.
Yeah, right, exactly. But notice that there are many choices for the section. We just choose the mean value coordinates as a section, and there are a lot of other choices. So we don't know, like given any two geodesic triangulations, there might be a lot of choices for the morphing, and we don't know whether which one corresponds to a geodesic in which sense. So that's definitely a very interesting topic to explore. And especially, I think probably in the computational side, one interesting question to ask is, we really want to get some control during the morphing, right? We want to say something about the angle will not get bad during the morphing, and edge length is going to have a lower bound during the morphing. So right now, this kind of question is completely open.
Yeah, I mean, one other question, if I could. So you had a spring energy model that you referred to, but you can modify that to any exponent. So you could have not just a quadratic energy. And I was interested whether you've looked at the L1 norm, which would just be the perimeter function.
Not really. Yeah, I'm sorry, I don't know anything about like by L norm. You mean like the sum of weighted sum?
It's just
of
the lengths, because
okay.
then it begins to look like like a discrete mean curvature flow. If you're thinking about evolving in that energy landscape.
Okay, so yeah, I never tried to explore that problem, but I guess for the surface negative curvature, probably the distance function is still convex, so you can still at least guarantee that you can have a unique minimizer. But yeah, we don't know what happens in that case, whether that's embedding or not.
Yeah, super, thanks.
Any other question? I'll ask one. It's related to a comment, Yanwen, you just made. In the morphing situation, you rightfully do the interpolation in the weight space.
Mm-hmm.
And you know that this weight space is convex, you can do that interpolation.
Yes.
But once you have the weight, the interpolated weight,
let me go back 2 pages, I guess. Okay, here.
Yeah, this one. Now that you have the new set of weight, W subscript T.
Yeah, right.
You have no guarantee on the triangulation, do you?
That's exactly the Tutte embedding theorem we generalize, right? So Tutte embedding theorem says that for any given such a weight, if you can find the W balanced map, that will definitely be an embedding. But probably you mean some geometric property for this embedding, right? That's
I was looking at geometric property. Could that be a way to improve a triangulation?
And for that, we don't know anything about that part. We can only show that the result is indeed embedding, but we don't have any quantitative like analysis about what kind of angles you can choose. And that's actually sort of determined by how do you do this linear interpolation, right? Just like as I mentioned, like probably we want to do a linear sort of interpretation such that the angle will not distort it too much and edge length will not change too much. So here we don't even need, we don't even know this question in the planar case. So I guess hyperbolic case is gonna be the second problem I'm gonna look at. The first case gonna be definitely look at the planar case. Yeah.
And interestingly, my question was aiming at the planar case. I wasn't thinking of the high genus surfaces. But I think you answered my question in that we don't know more in the planar case than we know in the high genus.
No, there are some choice like quite technical. They are moving these vertices in like individually, like one by one in each of the stars to make sure that the angle is not small enough. So in this sense, you are choosing the weight like a piecewise straight lines in the space weights, but that's still sort of probably not as good as our expectation. We really want one way to do the linear interpolation. Yeah.
Any other question for Yanwen?
Oh, David.
Oh, David, yes.
Hey, Yanwen, it was
Hi,
nice.
David. Thank you.
I was wondering if you thought at all about other ways of associating a weight to a triangulation. Like, so you have this, so you have this is the picture that I actually was interested in. So you're taking the triangulation and you go up to the weights and you have a particular section in mind. But do you know anything about that sort of bundle, like the possible weights that give the same triangulation?
Yes, that's a very nice question. Actually, if we think about the planar case, let's say we fix the geodesic triangulation and we ask what are all the possible ways such that once we solve the Tutte embedding theorem, that will give us this particular geodesic triangulation, right? Is that a question you want to ask?
Yeah, that's exactly the question.
Yeah. So that space is definitely, in some sense, a linear or affine space because you are basically solving. So probably let me go back a little bit. You are basically solving this matrix from the realization, right? You know what are, this time you're not solving X, you know what are X and Y, you're solving those weights. So you can see that you have some linear constraints for those weights, right? So yeah, everything is gonna be linear here. All the Xi's and Yi's gonna be given to us. So that will definitely be a sort of finite dimensional affine, I will guess, affine space, some sort of subspace in the Euclidean space. But we don't know that. There are some, so I should say that when we try to solve this contractibility problem, we really want to make sure that the space is large enough so that we can really lift everything and do linear interpolation like that. But this space, I guess that's all I know, like a fine structure, a fine space, like some subset. It's still I guess that's a convex subset in the Euclidean space. But I don't know any sort of a characterization of this space other than this linear system. And there are multiple choices for this lift, like Floater actually proposed another one by taking the average. You look at the star and taking the average of you look at the star and look at the three boundary vertices once a time and taking average of what you get by the barycentric coordinate you get. And that's one thing you can do. And another thing is, in this space you can show is a convex set, so you can choose the center mass of this. But other than that, I don't have any characterization for this space. But this is the sort of a question we want to ask. We just proved the contractibility, so we want to improve this to like what do we have, what Bloch, Connelly, Henderson proved, like the homeomorphic to the Euclidean case. We know the contractibility is different from homeomorphic to the Euclidean space. So if we can prove this sort of a bundle structure, it might be possible to improve that from the contractibility to homeomorphic to the Euclidean space.
Great, thank you.
Yeah.
And Yanwen, just the very technical here. Maybe I missed it at some point. You mentioned initially when you were looking at Tutte's theorem that the weights may or may not be normalized.
Yes, right.
Does that matter after?
It doesn't matter.
It doesn't matter.
It doesn't matter.
Because the difference is going to be the one on the diagonal.
Yeah, right. You can just take the sum of all the W1, 2, 1, and 3 and put that in the diagonal. That will be the original matrix. Yes. So putting 1 here is sort of a convention I saw in the paper. So yeah, but that's really not necessary.
There's a question by Fang.
Oh yeah. So it was a nice talk. So have you thought about, link your work with the talk that Chris gave this morning? He mentioned it, this measurable Riemann mapping theorem is extremely powerful. That theorem implies immediately that the space of all quasi-conformal map of a disk is contractible, of any closed surface is contractible.
Yes.
And what you're doing seems to be saying
exactly. Yes.
If you have a piecewise homeomorphism, then the Beltrami coefficient is a constant, step functions on the triangulation.
Exactly.
You thought about discretize these measurable Riemann mapping theorems. That will, if it works, that will be fantastic.
Definitely, that will give an immediate proof of this fact. Actually, I tried this idea. So this happens when I was a graduate student at UC Davis. I asked this question. Asked Misha Kapovich about this question, and he thought about that like one day, and the second day he asked me to try this. So you just think about the discrete version of the Beltrami coefficients, and you do linear interpolation in that space, and you check. Beltrami coefficient basically just like we have a linear map from one triangle to another. That will give us a unique Beltrami coefficient, right, given by probably the ratio of the two singular values. And then we can do linear interpolation for each of the phase. And the target will be, of course, 0. And the probably initial point are going to be the initial geodesic triangulation. And then the question is, if we just do this when we try to glue those linear map or those linear like geometric triangle together, the problem is the coin points might occur. So you look at each vertex, the angle sum will not necessarily to be 2 pi. So I actually find a very specific example, but unfortunately I already forgot that somewhere in my notebook. So if you start from one particular figure and then try to compute the linear interpolation of the Beltrami coefficient, actually after a certain step, you're gonna have a coin point generate. So that's the main issue. You are going outside of the geodesic triangulation because you're gonna have a coin point on your surface. Yeah, but definitely that would be a very natural idea to try to see whether the space of discrete version of Beltrami coefficients is contractible in this study.
Right. I don't know, Chris. He's here. Has people in complex analysis ever thought about discretize measurable Riemann mapping theorems and do something like piecewise linear?
Yeah, well, I've thought about it a little bit myself. In fact, if you were to look at one or two of my recent NSF proposals, I proposed a problem about solving a discrete measurable Riemann mapping theorem on triangulated surfaces. It's something which I proposed, but I've never gotten around to actually getting to. The problem is just what he said, that if you sort of do the obvious things, you're going to get to situations which don't arise from a triangulation. They arise from a topological triangulation, but at the points where the curvature isn't quite correct, instead of having straight lines meeting, you're going to get infinite spirals which come in and meet at a point. And so the triangular things can become twisted in a certain way. I had I visualized a way of getting around that. It had to do with thinking of discrete curvatures being concentrated at the points as we've seen, and then sort of diffusing the curvatures from one point to another by sort of an averaging process. And I'd sort of this thought in my head and said, oh, this is always good, be good to come back and think about carefully and write it down, but I sort of never got to that. So, so I've thought about it, but I've always been intimidated by the fact that lots of other people, like most of the people at this conference, have thought much more deeply and carefully about a discrete differential geometry than I have. And I guess I figured if it was doable, they would have done it. But yeah, I am probably some other people. I don't know anyone else, but I've thought about it myself, and it's sort of on my list of things to return to. This is unfortunately a list which tends to expand rather than contract. But yeah, that's all I have to say on it right now. I'd have to even review my own notes to say more.
Thanks.
So Joel, you had raised your hand.
Yeah, so my question is, so you prove this discrete contractibility completely independently of the smooth contractibility, and the question is, does it give a new proof of the Earle-Eales theorem? Can you limit? Can you prove that can you prove the smooth case by taking finite and finite triangulations?
Yes, I think I told you this before. So in the let me go back to this page. In the planar case, indeed, it's pointed out by Bloch, Connelly, Henderson that if you can prove the discrete case, you can prove this homeomorphic to the Euclidean case, then you can use some machinery in algebraic topology to prove that in a smooth setting, the space is indeed contractible. So, but honestly, I'm not familiar with those machinery in algebraic topology, so I don't know that. Probably it's gonna work, but yeah, I'm not sure about the question.
Okay.
So taking some inverse limit, I guess, for those homotopy groups.
So I guess if there are no more questions, and I don't see any more questions, we're going to thank again Yanwen for this interesting talk on the space of triangulation and its contractibility.